Hey gang, so just a quick video over some of those guidelines to effective data management from the Bohr et al. Paper. Remember, this was published in the Bulletin for the Ecological Society of America back in 2009, and it's just 13 guidelines for effective data management. I just wanted to run through those quickly and then give you an example of how to do some of this stuff in R. So the first of the 13 pointers they give is to use a scripted program such as R to store and analyze data. And they point out that this provides a written record of steps that you take when you're either cleaning the data or transforming the data before you analyze them. And this provides an analytical metadata or step-by-step of how data, the raw data, were treated, which can be useful in terms of sharing what you did to promote transparency or reproducibility. And later in other lectures, I'll show you how to use R Markdown to do that really effectively. But today we'll just stick with the basic R coding in an R script. The second is to store data in non-proprietary software formats. So proprietary software may not be available to all users. You have to pay for that, and so some budgets may not allow for that. And then the other issue is that proprietary softwares tend to change. So think about the file extensions in Excel that have changed over time. XLS versus XLSX, for example. But .csv or .txt files will never change, and they don't have this issue. And so I always encourage my students to use CSV files. The third pointer was to use non-proprietary hardware. So many of you have probably never used a floppy disk. Some might remember hard disk or zip disks. But now even CDs are not necessarily supported by all hardware. So look at the computer that you're using right now. Does it have a CD drive in it? In most of the newer ones do not. And what Bohr and others suggest is to use the internet or the cloud to store data so they can be downloaded remotely onto machines regardless of the hardware that's available. And for this class, we'll use Canvas as a way of storing and sharing data. But a lot of the journals that you might submit your data to have online data storage facilities. The fourth pointer is to store the uncorrected data file and then process all of the steps that you need to get the data ready for analysis in R and annotate the steps as you go through them. And this is a way of just tracking how you have changed data or had to transform data so that it's a reminder to yourself. And this is the same idea of providing an analytical metadata. So RStudio in writing in annotations to yourself is what we'll focus on. The fifth pointer is to use descriptive names for data files. And there's a trade-off here because longer names can contain more information, but they require a greater number of keystrokes. Shorter names require fewer keystrokes, but you may unintentionally omit critical information. And so naming files is something that you'll get better with practice. It just comes with doing it. Today we'll go through using either underscores or camel caps, where you push two words together, but you capitalize the first letter in each of those words so that as you read through it, each of those words tends to stand out. Okay. So avoid spaces is the main point there because this can create some issues in R. Including a header line to describe all of the variables is critical. So each column will represent a different variable, and you'll want the very first row to include the name. And I'll show you today how to exclude that header row from the data when you're doing your analysis. So you can make notes to yourself about what the columns represent, and then you can exclude those notes from the analysis. The seventh pointer is to use this American Standard Code for Information Interchange, or ASCII, maybe you've heard of that. And this is because most softwares, including R, do not support accents or tildes or even ideograms. because it was built around simple fonts, and ASCII is probably the simplest one. So we'll only use letters, numbers, hyphens, and underscores when we name files and variables. We won't use anything more complex than that. The eighth pointer is to always add rows and not columns to a database. This requires a little bit of forethought when you're first creating the outline for a database as you build it, but you'll want all of the pertinent information to be represented by a column, and then in columns. And then as you enter observations, those should be rows, and so you grow it across rows instead of adding new columns every time. Sometimes it's unavoidable to have a blank, equipment malfunction or a missed observation. You can put placeholders like NA, and I recommend using capital N, capital A as a placeholder when you need to leave one cell blank, or otherwise would have left it blank, or it's missing information. So here's an example from this Borer et al. Paper. So imagine collecting vegetation biodiversity data from a site in Corvallis in 2006. Here's this first row is the header row that gives information about what's in those columns. So this column is site information. This is species 1. These numbers might represent abundances for each of those species across those sites. Then you go back to the same location in 2007, and perhaps you collect a larger number of species. So you'd have to add another column there in order to enter data from 2007. The better way to store these data would be to have a column that represents date, so the year of collections, the site, the species name, and then abundance. And here it's much more clear that the values represent abundances because we have a header there that's called abundance. Okay? So just giving a little bit of thought before you start entering data to think about long-term data storage and building a data set out over longer time periods. So for example, if we wanted to revisit some of these sites in 2021, we could just enter the year, the site, and then the species that we encounter in the abundance for each of those. Okay, so we'll give an example of this in the lecture today using some fish. The ninth pointer that they give is each cell within a column should contain only one type of information. So avoid merging cells. The example that they give here is this note that the following data were collected by EB students. And notice there's missing data from here, and then the number of columns in this row is only 2. And then you go to the next one and the number of columns goes back to 6. And so the better way of storing data like this, if this information about who's collecting the data is very important, create a column called notes or data collectors, and then put EB versus non-EB, for example. So you want to avoid this issue of not having information in every cell, and then only having one bit of information in a cell. Okay. The fifth they suggest is a single piece of data only once. And so I'm going to give you an example today of 2 tables, one that includes site level information and then one that includes species level information. And in the species level information table, site is given there, and maybe we know the day that we visited those sites, but we might really only want to enter that information once in this table about site level information, and then we can link those together. And what this does is reduce wasted space. It avoids having to restructure the data when you want to analyze them. It reduces redundant data entry and reduces the chances of inconsistent data if you were to maybe enter the wrong value for one of the multiple times that you are entering something. Okay, so I'll give you an example of that one momentarily. 11 is for the ecologists that are studying species, record the full taxonomic information. So use the binomial nomenclature. And even further than that, if you want to be really sure that the species information will be useful in the future, is you could give the authority that described it in case a species redescription comes later or species are split out. So humans, Homo sapiens described by Linnaeus, or the small eye shiner, Natropus buccula, described by Cross. These are just examples of using underscores to give genus, species, and the authority. And so in today's example, we'll do the genus underscore species designations. The 12th pointer was regarding time, and time can be really tough to deal with, especially if you're from the United States, where we tend to show, when we write out a date, we might give the month, the day, and then the year. But most of the world gives the year, the month, the day. So starting with the most significant component and going down to the least significant component. And you can extend that into hours, minutes, and seconds. And what they suggest in the Borer paper is to always give 4 characters for the year, 2 for the month, 2 for the day of the month, 2 for hour, 2 for minute, and 2 for second. Okay, and I'm going to show you how to enter these data. It ends up being a very long string of numbers. And sometimes you don't need, if you're not recording hours, minutes, or seconds, you may not need to go down to those lower significant units. You may only need the year, like that example I gave you earlier. But if you want to be really consistent, you can enter all of these data. And then the very last pointer that they give is to always maintain metadata. So data about the data, that's what that term meta means. And so this is a way of sharing your data with other users so that they understand what each of the variables means and how those were collected, or maybe a reminder to the future version of yourself. If you put a data set down for a while and pick it back up. In the paper, they say, do not underestimate your ability to forget details about a study. And even over a short time period, like a couple of months, you may forget details that are pertinent. And so storing a metadata file that may or may not be what you read into R, it could be a separate data, sometimes a Word document or a CSV file that just gives definitions about what the data represent, and then maybe how they were collected, okay? And a lot of journals and online data repositories require you to provide metadata when you make a deposition. So just with the idea of keeping this rather short, let's just go through an example for how you might typically enter data, save those, and then bring them into R. And what I've noticed is that most students store or enter their data with Excel. And so we'll just go through an Excel example here. And remember, we don't want to store the data in Excel. We do want to convert that to a text file or a CSV file. But typically what I've noticed, and even in my own research program, we start with Excel, Access maybe another place where you're storing data. So let's just start with a simple table that has a column that represents a site where we might visit and collect fish. And then we might want to track the time that we visited that site. Okay, so we'll say, so there's our header row. And then we'll say site number 1. And the time that we visited that, we'll give the year, 2021. We'll give the month, February. We'll give the day, the 7th. Notice I'm giving 2 digits for each of those, even though the second month could be designated with just a 2. For consistency, we'll put a 02 there. And the same thing with the 7th day of the month. 07 is the most consistent way of doing that. And say we visited a site at 10:30 in the morning, so the 10th hour, the 30th minute, and then 0 seconds, okay? And notice that Excel automatically lists this using scientific notation. And what you can do is right-click, format cells, change it to a number with 0 decimal places, and you should see this long string of numbers. Okay, so we'll just enter 3 sites here. So if you want to follow along with me, so site 2, say we visited that during 2021, the 2nd month, the 7th day, but 1400 hours. So we're using military time, as you may have heard of it. Just so 12 o'clock, and then 1 o'clock becomes 1300. 2 o'clock in the afternoon would be 1400 hours, and so on. We'll say we're 30 minutes into it in 0 seconds, because maybe we didn't collect seconds, but we want to go ahead and put a placeholder in there. All right, and let's do one more. So we'll say we visited this one on the 2nd month on the 8th day. So maybe data collected on the next day from the first two sites. And so we might be 10:30 in the morning with 0 seconds, okay? So long string of information there for time. Time is the one that probably will give you the most headaches, but there's an example of how you might enter that. Okay, so then you can just select File, Save As, and I'm going to save this in a folder that's related to week 3 for this class that I'm teaching. So then you can save it as, and just choose this first one, comma separated version or a comma delimited file. And I'm going to call this one Site. So I'll just click on Site and Save. And I had already saved this when I practiced this lecture earlier, and it says, do you want to replace that? And I'm just going to click yes, that I want to replace that. And then when you make a CSV, it always says, do you want to keep using that format? And an important consideration here is when you're using multiple tabs in Excel, and then you save that as a CSV, it only saves the active tab. And so, you know, there's this safety in place that asks, are you sure you want to use CSV? And one of the things you need to think about is, do you have multiple tabs going, or do you just have a single tab? And so we only enter data on a single tab. And so I'm going to say, yes, I want to keep using that format. So it saved it. And the other thing that the CSV files do that's kind of annoying is if I go to close this now, it's going to ask if I want to save any changes that I made since I saved it last. And I didn't make any changes. So I'm going to put don't save. And what that means is it's going to keep the file. The file is still there. It's just not going to save any changes between my initial save and this closing down of the file, okay? So let's make one more file. I'm just going to open Excel again and just click on an empty spreadsheet. And this time we're going to make a file that is fish abundances from each of those sites that were visited, okay? So we're going to have a site column again. We're going to have a column that's fish for the genus and species. And then we're going to have a column that's abundance, the number of individuals that were collected. And in my lab, we typically use seining as a way of collecting fish. Okay, so we'll say site 1. We'll say the species that we collected first was Gambusia affinis. So we're using the genus and the species, and we're using an underscore between those. And then say, for example, we collected 30 of those individuals. At that same site, we might have also collected a second species. So we'll say site 1 again. And then we'll say the second species, Cyprinilla lutrensis, the red shiner. And maybe we collected 70 of those individuals. So we're not using common names, we're using the genus and species because common names can change, or there may be multiple common names that are used for the same genus and species, okay? And say maybe we caught even a third species at that same site. So notice it's 111 for the site because all of these species were collected at the same site. And maybe this one is Pimphales vigilax. And say we collected 18 of those as the abundance, okay? So we're building this out in what we refer to as long format. And I'll show you later in the semester how we can transform that into wide format, into a site by species matrix. But when you're first entering the data, it's best to do it in this long format. So notice we haven't been adding any columns. We're just adding rows as we start to build out this database. So let's say we go now onto the second site and we encountered Gambusia affinis again. And at that site, we collected maybe 12 of them. Then we go on at that same second site, maybe we also collected Cyprinilla lutrensis again. And maybe there was 4 of those individuals of that species. Then we could go on to the third site, and maybe there we collected just Gambusia affinis, and there's 73 of those individuals, okay? So you can imagine as you start to visit more sites, you can build this database by just adding rows, and we're not having to add any additional columns, okay? And when you've finished that, you can save that. So I'm going to say File, Save As, go to that same place not save it as an Excel workbook, but I'm going to save it as a CSV file. I'm going to call this one fishes, and I'm going to click save. And because there was already one there, it's asking, do I want to replace that one? And I'm going to say yes. And because we built it in an Excel database, but we changed to a CSV, it's asking, do we want to keep using it, saving it as a CSV? Remember, if we have multiple tabs, you're not going to want to do that because you could lose any of the tabs that aren't the active tab. But since we only have one tab going, I'm going to say yes. I'm going to keep using that. So it saved it. And some time has passed, just a few seconds since I saved it. And so now if I click close, it's going to ask if I want to save it again. And I'm just going to say no. Okay. So then we can go into R. We just used Excel, which is proprietary software to create that. But then we transformed it to a CSV so we can share it widely and it's non-proprietary. So in RStudio, I'm just going to click on this plus symbol here to create a new R script. And notice that it pushed the console down. And I'm using version 4.03, this bunny wunny freak out. So here, the first thing that we typically want to do when we want to bring data into R is to set what's called the working directory, or the file path that R will follow to search for files as we read them in. And so we can annotate the code and say set working directory. And my favorite way of doing this, there's multiple ways of setting the working directory, but I like to go to session, I like to go to set working directory, and then I like to choose the directory. And what I just did there is what's referred to as a graphic user interface. There's not going to be necessarily a record in our R script of what I just did, but I'm going to show you a way of saving that. So I'm going to go back to week 3. That's where I saved those CSV files that we just created. And I'm going to select open. And what I want you to notice is nothing changed up here in our script, but down here in the R console, we have this function set WD, set working directory, and then it gives a file path to where I just navigated. And what I like to do is copy that and paste it right there. And so now every time I open this R script, it's going to have this set working directory function, and it's going to have that file path already entered. Okay. So an alternative way would have been for me to use this function set working directory and then remember the file path. But I found it's much faster to just use the graphic user interface from RStudio and then copy and paste the function that it automatically puts into R. Okay. And then we might want to save this R script. So I can go File, Save As, go back to the same week 3, and maybe I'll save this as week 3 coding example. And when I do that, what I want you to notice is this red text with the asterisk next to it that represents the fact that I have not yet saved that R script. It's going to change, and it's going to change to the name of what I just named it, and it's going to change to black text and drop that asterisk, representing that it has been saved. Also, this save icon here, these disks that we were just talking about, is not existing. It's not hardware that exists anymore. I want you to notice that that turns to a light gray color. It's not a selectable icon. It's representing the fact that I have saved all of my current work. Okay, so I'm going to click save. All right, so the text changed, the color of the text changed, the asterisk is gone, and the save icon is now unselectable. But if I make even one change, if I hit enter right there, notice it went back to red. It has the red asterisk there, and the save icon is selectable again. If I just click save, it goes back to black text and the asterisk goes away. So that's RStudio's way of reminding you to save your work. Okay, so we have set our working directory. So now when we try to read in data, RStudio is going to know where to look. It's going to follow that file path. So the next thing that we might do is to just annotate the code and say read in data files. Okay. And then I'll go to the next line. And here we've got to name these. And this is where this idea of naming with short names is important. Short enough that it doesn't require a lot of keystrokes, but long enough that it's meaningful to us. And so because we're using a very simple example here, I might just call this first thing sites. Then I'm going to use the left arrow. Remember in previous lectures, we said you could use an equal sign there, or you can use this left arrow that's created by the less than sign and the dash. And I always like to use the latter there because sometimes within the functions, you'll use an equal sign. And so we're not using equal signs in multiple places this way. And so we're going to use read.csv in the utilities package that's automatically entered or automatically loaded with R. Okay, we didn't have to jump onto the CRAN yet to download a package. I'm just using a function that's automatically loaded, this read.csv. And then we just need to tell it the name of the file. So I called the first one sites.csv. Notice I have to give the extension there. And notice I gave that file name within quotations. Okay, so I'm just going to run that. And notice what it did. So when I hit run, remember that pushes it down to the R console. It automatically shows the line of code there. And in our environment, it created this thing called sites that has 4 observations of 2 variables. And I can click on that. And what I want you to notice is that it's got site and time there are columns. And then it's got the site number and the time here expressed as in scientific notation. And I'll show you how to format this later on into time, okay? We're just gonna take a few steps at a time. There's another argument that we could have put in there, which is comma header equals true or capital T. You could spell out true in all caps, or you can just put a capital T. And if we run that, what that does is it designates this first row as the header. But what I want you to notice is actually the function recognized that that was a header and had already done it. So some of you that have been coding for a while, maybe you're used to having to specify header equals true. You actually don't have to do that anymore. Okay. And if I continue to click that, it's just going to continue to overwrite what's there. Okay. So the other file that we made was called fishes, and I'm just going to continue with that name. We'll use the same read.csv. We'll do quotes around fishes.csv, and then we can run that. Oh, notice here that I misspelled fishes, which is actually quite embarrassing as a fish ecologist. But when I did that, I get an error down here. It says cannot open the connection. In addition, warning messages, cannot open file. It gives the misspelling that I gave. No such file in directory. And so you don't want to ignore those error signs or error messages because what that's basically telling you is it wasn't able to load it. And it's all because I transposed the H and the E there. And fishes, incidentally, is the term that we use when we have multiple species of fish. It's the plural for at the species level. So I'm going to click on that and run it again. Notice that time it worked. I have this object called fishes here. It's got the header automatically in there, site, fish, abundance. Here I use the word fish to represent the species. We could have easily used the words genus, species there, but it's our site. It's the species, it's the abundance. All of the data are in there. And we didn't have to enter the time that we visited each of these sites because we have that in the second table. And the last thing I'll show you, I'm just going to hit save here. The last thing I'll show you is how to merge or join those two together. And that was one of the pointers that Bohr et al. had given. Don't enter the time that you visited over and over again. Do it as a separate table and then join them together. And so we can say just annotation, join or merge fishes and sites. And to do this, what we can call this the joined underscore data frame, which is a description of what we did, but not necessarily informative about what that represents. What we might actually want to call that is fishes, sites, data frame. Notice that required a little bit more, a greater number of keystrokes, but perhaps it's more meaningful. And actually, if we merge those things together, it'll create a data frame automatically. So maybe we could just call it fishes_sites. Use the left arrow, and we'll use the merge function from the base package. And here, we're just going to merge fishes and sites. And then we just have to tell it a common column that exists between those two. And remember, in sites, we had site, and then we had time. And then in fishes, we had site, fish, and abundance. And so because we have that common column between the two, which we called site, we can join those two tables together by that common feature called site. Okay, and those are the three arguments that we'll use for merge. And if we run that, notice we get this new object called fishes_sites. It's 6 observations of 4 variables. Here we had 3 variables, here we had 2 variables, but in each of those, site was one of the variables. So it doesn't repeat site, it puts site in there, it gives us fish, it gives us abundance, and it gives us the time, okay? So we can close this, hit save, and there's a very brief introduction into how you might enter data, save them as a CSV, read those data into R through RStudio by linking through your working directory, and then how you can merge those data together, okay? And we'll build on that complexity as we move through the semester. See you later.